ANSYS ICEPACK is ANSYS's electronics cooling solution. This webinar will cover Release 18 enhancements to ANSYS ICEPACK's capabilities in printed circuit board electrothermal analysis, chip thermal model or CTM import and back annotation, MCAD workflow, meshing, solving, and high performance computing or HPC, as well as ECAD handling, post-processing, and electronic component XML support for data exchange. Towards the end of this presentation, I'll also introduce the upcoming ANSYS Electronics Desktop ICEPACK. This is an exciting new offering from ANSYS, and I'll give you a peek into what's coming down the road. So first, I'm going to go into the topic of ICEPACK enhancements in the area of printed circuit board electrothermal analysis at Release 18. There were a number of enhancements in this area, so I'm going to spend some time in detail going through these enhancements. So we see electronic components with smaller footprints and higher power requirements. And increases in current density lead to increased joule heating in traces, planes, and vias and board. This joule heating further affects the electrical performance of the PCB or package substrate. Additionally, different component properties and temperatures also affect the mechanical reliability. So there's three areas of reliability concerns in a typical PCB design. You have electrical reliability, thermal reliability, and mechanical reliability. ANSYS's printed circuit board multi-physics solution workflow addresses these three areas of reliability concerns. This slide shows a schematic of the ANSYS PCB multi-physics workflow. The starting point is a electrical DC analysis in ANSYS SI-Wave. This will give you conductive losses in the board and a very detailed picture of those conductive losses, layer by layer and spatially varying at each layer. These conductive losses are then transferred into ANSYS ICEPACK, where a thermal analysis can be performed based on those losses. The result of this is a temperature map in the board. This temperature map is then transferred back to SI-Wave, and with these updated temperatures, a new SI-Wave DC voltage drop analysis can be performed. And this is highly dependent on temperatures, so you want accurate temperatures when you're performing this DC-IR analysis. So with this new SI-Wave simulation, you can transfer the new conductive losses into ICEPACK and get a new temperature map. And so this process iterates until convergence. Once you have thermal convergence, you can then move on to the next stage of the analysis and consider mechanical reliability. So using SI-Wave and ICEPACK gives you a bit clarity on electrical and thermal reliability, and then you can transfer that converged temperature map in ICEPACK into ANSYS Mechanical and perform a thermal stress analysis. And this will give you deformations in the board based on thermal gradients. So this is ANSYS's PCB multi-physics solution workflow, and it's very well established at this point. There's additional information on this workflow. There's an abundant amount of information on ANSYS's website, in the customer portal or under knowledge resources. So there are two options for the printed circuit board electrothermal analysis part. The first option is launching the IcePack SI-Wave coupling from within SI-Wave itself. That's option one. Option two is launching the SI-Wave IcePack coupling from within IcePack. So you can kick off this coupling, this electrothermal coupling from either SI-Wave or IcePack. And whether you go one way or the other depends on your starting point and your preference. Both options are fully automated and iterate to thermal convergence. The key difference between the two options is that if you kick off this electrothermal coupling from IcePack, you have more flexibility in building up your thermal environment, and you can set up any arbitrary thermal environment that is necessary. So you can include fans, enclosures, any combination of IcePack objects or mechanical CAD. In SI-Wave, on the other hand, you'll get a quick picture of your thermal performance, but it'll be for more simple thermal environments. So the key difference there is that IcePack, launching this coupling from IcePack gives you more flexibility in building your thermal environment for the board. And whether you go one way or the other depends on your end goal. So what I want to talk about today is the enhancements that were made at Release 18 for both of these options. I'll spend some time on this, and then I'll move on to the other areas of enhancements. So first, I want to talk about option one, that is launching your electrothermal coupling from within SI-Wave. So when you're in SI-Wave, you can see this ribbon here on the top, and you can click on the simulation tab there, and there's an IcePack icon. And click on this, and you can begin setting up your thermal portion of your electrothermal analysis. So when you click on IcePack in SI-Wave, the SI-Wave GUI launches the IcePack solver for you. And again, this is a fully automated iterative coupling between SI-Wave and IcePack for DC-IR electrothermal simulation convergence. So joule heating power profile maps go from SI-Wave into IcePack, and temperature maps go from IcePack to SI-Wave. What you'll see in SI-Wave is this tabbed panel open up. And this tabbed panel walks you through your thermal environment setup. And you'll notice that on the first tab, simulation setup, there's thermal simulation type. And you can click conduction for a thermal conduction only simulation, or you can click convection for a full CFD simulation. If you click conduction, your simulation will be faster. If you click convection, it won't be as fast as conduction, but it will still be relatively quick because it's a simple convection environment. In particular, it'll be a computational wind tunnel. So you'll just have a flow going over the board, and you can optionally include components as well. The next tab in this IcePack simulation setup panel is thermal environment. So if you chose conduction as your thermal simulation type, you can then select appropriate thermal boundary conditions. And IcePack will, based on your inputs, IcePack will calculate heat transfer coefficients based on established correlations. That's for conduction. And then for convection, based on your inputs, SiWave will set up an ice pack simulation with your inputs as boundary conditions. The next tab in this SiWave GUI workflow is the component configuration. So you can add components selectively here, and you may not want to include all components. So you can put a check mark for whichever components you want to include, and then you can assign appropriate powers to those components. These will be included in your ice pack thermal simulation. There's also a filter option, so you may want to use this if you don't want to overburden your thermal simulation with unnecessary components. So you can filter all RLC components below a certain power, and this will reduce your computational requirements in ice pack. On the fourth and final tab, this is available when you're doing convection type. So you can create the overall dimensions of your CFD wind tunnel or ice pack cabinet in ice pack terms. There's a button here to apply a recommended size. So this just applies some recommended size and puts some inputs in here. So that's how you would set up your electrothermal simulation from within SiWave. What ice pack can, or what SiWave can do for you now is allow you to post-process your temperatures from within SiWave itself. So after setting up your SiWave, after setting up the simulation in SiWave, an ice pack project is built and run in the background, and at that point, after the simulation is complete, you can post-process your temperature fields directly from within SiWave. And you can now create cut plane temperature post-processing objects within SiWave. And before I get off the SiWave-based workflow, I'll mention a couple more items in terms of enhancements at R18. Updated mesh settings were implemented in ice pack for improved solver stability. So when you set up your ice pack simulation in SiWave, there'll be some default mesh settings already set up in ice pack, and these have been improved at 18 for improved solver stability. Also, a noteworthy enhancement is the spatial profile implementation for the layer-by-layer power dissipation maps. And this has resulted in major improvements in overall turnaround time and robustness. And I'll talk a little bit more about this enhancement when I start talking about improvements on the ice pack side of this workflow. And finally, a useful tool is this ability to create and open an ice pack project from SiWave. This allows you to go on and perform more detailed analysis and reporting in standalone ice pack. So previously I was talking about going to the simulation tab, and this allows you to perform the electrothermal simulations. But if you just want to export your board into ice pack, then you can go to this export ribbon and click on ice pack, and you set up your ice pack project in a very similar way to what you would do for the simulation. And this won't solve it won't kick off the solver, but it'll set up your ice pack project, and then you can go into ice pack and add whatever kind of thermal environment features you want to include. So this allows you to go from SiWave into ice pack without immediately solving. So that kind of concludes the portion on enhancements at R18 in the SiWave-based workflow for PCB electrothermal analysis. So now I want to give you some updates on enhancements for Release 18 for the ice pack-based workflow, or option 2. So one area of improvement is in terms of usability. The macro that launches the electrothermal analysis in IcePack now only requires pointing to the board in IcePack and the SLA project file. So minimal inputs are now required at R18. Speed and robustness improvements. So as I mentioned previously, we now implement a spatial profile for the power dissipation map. And we use a PCB primitive in IcePack. And this has resulted in major improvements in overall turnaround time and robustness. Additionally, boards can be offset or rotated from their original location, and temperatures are mapped back to SLA accordingly. So previously, you needed to keep the board in IcePack in the same coordinate location as it is in SLA. And then you need to kind of build around it in IcePack. But now you can click the Certify Trace Transform button or check mark, and you can move your board in any fashion you'd like. And IcePack and SLA will understand that and transfer power maps and temperature maps accordingly. And also, I want to mention that this workflow now has support for multiple boards. So boards of the same setup can point to the same initial SLA project here. The macro will launch an initial run, create the individual SI temperature files, and then queue the individual launches of new SLA projects. Here, each board or substrate must have a separate SLA project. So that kind of summarizes the enhancements at R18 and the PCB thermal analysis capabilities. Now I want to talk about enhancements in IcePack's capabilities to handle the chip thermal model and to back annotate temperatures to ANSYS's semiconductor tools, such as RedHawk. So at release 18, IcePack can directly import the chip thermal model, or CTM, that is generated by ANSYS RedHawk. And the workflow here is pretty simple, and the schematic is shown. So you can directly import that CTM, and then you can directly send back your temperature maps. So you can directly export a back annotation file to ANSYS RedHawk. And this allows you to perform a thermal-aware electromigration reliability analysis on the chip. So direct links both ways here between ANSYS RedHawk and ANSYS IcePack. This is what the import panel looks like in IcePack for CTM import. And this is what the export portion of this workflow looks like. So you go to main menu, report, export, RedHawk back annotation. And this allows you to export the temperature at each tile to RedHawk for a thermal-aware electromigration analysis. The next area I want to talk about is enhancements to IcePack's capabilities at R18 in its mechanical CAD workflow. So there's been significant enhancements in IcePack's capabilities to handle mechanical CAD data. And the key reason for these improvements is IcePack's linking to SpaceClaim. ANSYS SpaceClaim is the new de facto CAD cleanup tool for all ANSYS products. Geometry simplification, repair, and modification is significantly streamlined compared to ANSYS Design Modeler. At release 18, most of the Design Modeler electronics utility or electronics toolbox capabilities have been incorporated into ANSYS SpaceClaim. So Design Modeler is still there, and for users who prefer Design Modeler, you can continue using Design Modeler or DM. But you can, for users who prefer SpaceClaim or who want to learn SpaceClaim, you can now use SpaceClaim to import your mechanical CAD geometry into IcePack. And the workflow in the Workbench project schematic is the same. You have that geometry module here, and you transfer your mechanical CAD into IcePack with that direct link to IcePack setup cell. In SpaceClaim, you can auto-identify simple IcePack shapes, and this is a similar feature as to what was previously in Design Modeler. After your initial geometry cleanup is complete, the Identify Objects button automatically can create simple IcePack shapes. So in this input geometry schematic, down here you have a few simple prism CAD blocks. And these are indicated in the SpaceClaim structure tree as CAD blocks. The Identify Objects command will automatically convert those CAD objects into IcePack prism blocks. And this allows you to bring them into IcePack and have the easy edit panel for IcePack blocks. So you can go in there, set up material properties, powers, boundary conditions on the block, etc. So you can convert your CAD into IcePack primitive objects, and you can automatically do so for simple objects in SpaceClaim. SpaceClaim now has these simplification levels, which were also a core feature in the Design Modeler CAD workflow to IcePack. So it's the same type of concept. You have 4 different levels. So level 0 converts geometry to a bounding box prism. Level 1 converts geometry to a collection of prisms and cylinders. Level 2 converts geometry to a polygonal approximation. And then finally, level 3 keeps the geometry as is. And you would use this only when needed. So you can take your original CAD geometry and simplify it using the simplify command, and also convert it to primitive IcePack objects. So you have the advantage in IcePack to have those familiar edit panels. In SpaceClaim, you can also modify the IcePack object type, and sometimes you would want to do this. So sometimes it makes sense to change the object type before you pull it into IcePack. So you may start with a printed circuit board, and you would simplify that, maybe at a level 2, and create an IcePack block, a polygonal IcePack block. But maybe you want to bring it into IcePack and have the advantage of using the PCB primitive. And this allows you to more easily set up things like orthotropic conductivity in the board. In that case, you would just convert it to a PCB object in SpaceClaim. You can also do this for 2D type objects in SpaceClaim. So you can convert an IcePack plate to a source or a wall or an opening, for example. So you may want to do this in some cases and convert objects before pulling them into IcePack. So SpaceClaim has a number of useful features now, and can be used very successfully in your MCAD workflow with IcePack. Next topic I want to go into is enhancements to IcePack's capabilities in meshing, solving, and high-performance computing at Release 18. So meshing robustness was improved in the area of CAD models in particular. So we looked at a variety of CAD models and improved the mesher in this area. Additionally, in terms of solver enhancements, IcePack now includes the option to disable radiation in fluid zones. So you can have thermal radiation be active throughout most of your model and then turn it off in specific fluid zones, if, for example, if it's a different type of fluid. So you would go to a block object, change that block object to be fluid type, and click on Disable Radiation there in that block. You can also now define your LED, light emitting diode efficiency, as a function of temperature. So as before, you would define your source as an LED source. And then under the edit, clicking on the edit button under LED power settings, you can define the efficiency as a function of temperature now. And this previously wasn't available until release 18. The Krylov reduced order model capability has seen some enhancements at release 18. So the Krylov ROM allows you to carry out efficient network modeling for your IcePack models. And we have more information on this in the customer portal. The key enhancement here at release 18 is that the Krylov ROM now supports source objects, block objects, and groups as inputs. So an increase in the number of inputs at release 18. The periodic boundaries object now has support for streamwise periodicity. Previously, it only supported cross-stream periodicity, but now it can also support streamwise periodicity. So this could be useful for handling fully developed flows in a pipe, for example. That's a typical application. You have inputs for mass flow or pressure gradient, and you can specify the bulk temperature of the fluid entering the system. You would check this to turn it on, or you would leave the option unchecked to model the default cross-stream periodicity. Improvements in IcePack's HPC performance at release 18 are shown through a test case, and the highlights of this HPC test case are listed here. So we have an IcePack model. It's a desktop server with mechanical CAD, electrical CAD, about 700 objects. The mesh has about 11 million cells using unstructured, non-conformal, multi-level, hex-dominant meshing. It was a steady-state solution with turbulent flow, conjugate heat transfer, and double precision solver. Some information on the system where these tests were performed is listed here. So these trials were run using IcePack 18 and IcePack 17 as a comparison. And each trial was run for 250 iterations. And the overall runtime includes the case setup and the iteration portion of the solving. So comparing release 17 to release 18, you can see here the overall runtime versus number of cores. And you do see an improvement at release 18 compared to 17. And at 17, we saw a similar improvement. So we're making strides here at each release to improve HPC performance and maintaining great scalability and leveraging the Fluent solver. You can see this picture a little more clearly if you plot it in terms of speed up versus number of cores, where the overall runtime for one core is taken as a reference to calculate speed up. So this allows you to see the improvements at release 18 compared to 17 a little better. Next, I'll talk about enhancements to ECAD handling in IcePack at release 18. So we have improved via modeling capabilities at release 18, and we're individually modeling the vias and no longer averaging the thermal conductivity. Additionally, via drill holes are now imported and modeled. So the via holes are completely modeled, and the effect of the electroplating and filling is accurately modeled, as they are no longer lumped. Additionally, when you're importing your IDF, you can bring in cutouts or holes in your board, and this is supported now through IDF import. And the boards are imported with fluid blocks for the holes. Now I'll talk about post-processing enhancements in IcePack at release 18. There are a number of post-processing enhancements, and they're listed here. solar heat flux reporting was implemented, optimized Manhattan displays, improved, and a Manhattan display is something you might create for, a chip power map, as shown on the bottom left here. It allows you to see a 3D kind of image of the power map or heat flux or even temperature. Improved surface probing, so you can surface probe on more post-processing objects. And you can also create smooth 3D contours, and there's now a transient option for full reports. So previously, a full report would only give you the final solution state for a transient simulation, but now you can view it at each saved point in that transient simulation. You now have the option to enable facet-based post-processing for object-face contours. So you can plot facet-based post-processing contours for temperature, heat flux, heat transfer coefficient. So all three of those variables. And so this is in addition to the standard nodal-based post-processing that's implemented already in IcePack. You now have this facet-based post-processing. And finally, the last enhancement I'm going to mention that was made at Release 18 in IcePack is support for electronic component XML or ECXML data exchange. IcePack can import and export ECXML data at Release 18, and supported features are the cabinet, plates, blocks, walls, sources, PCBs, grills, resistances, enclosures, heat sinks, 2R network blocks, and 2D and 3D fans, as well as solid materials, assemblies, and monitor points. So here a cross-platform encryption algorithm was implemented in a joint testing effort with Mentor. So if you want to, for example, import an ECXML file, you just go to File, Import, and ECXML file right here. So I've finished up the discussion of Release 18 IcePack enhancements. Now I want to shift gears into an exciting topic, in particular ANSYS Electronics Desktop IcePack, or AEDT IcePack. So I'm going to give you kind of a peek into what's coming down the road here with IcePack. And try to give you a good idea of the exciting new features that we'll be implementing. And this will begin at Release 18.1 in the form of a beta release. So here's just a quick disclaimer. You can screen grab it and read it later, but essentially it's just saying these are, this is just it's not a binding commitment. We're in the planning stage and there could be changes down the road. So with ANSYS Electronics Desktop IcePack, the goal is to create an automated, streamlined electrothermal multiphysics solution that utilizes native mechanical CAD and electrical CAD for first-pass mesh solve success. And we've received a tremendous amount of feedback for IcePack that we want to implement to give users a tool that will help them be more productive. And so the key drivers and mandates for this AEDT IcePack are listed here. We want to give users an improved user experience, a modern user interface, improved meshing and overall ease of use, and we want to allow users to have full integration into the ANSYS Electronics Desktop, as well as carry out enhancements on a quick and regular basis through rapid release cycles. So AEDT IcePack will be, will have an improved overall workflow. It will be a CAD-centric solution with a native MCAD modeler embedded, with geometry cleanup and simplification tools available within the environment. And it's a single environment for electrical CAD and mechanical CAD assembly. Also, as I mentioned before, we're focusing on improved meshing and overall ease of use. And another key feature here is we want IcePack to be fully integrated in a comprehensive electrothermal workflow. So IcePack will be embedded in the ANSYS Electronics desktop and be able to freely communicate with other ANSYS electromagnetic tools such as HFSS, Q3D, Maxwell, and SIWave, all in a single environment. So heat losses from your electromagnetic simulation can be easily integrated into your IcePack thermal simulation and vice versa. So as I mentioned, at release 18.1, it will be a beta release. So there'll be a limited feature set initially exposed. And this will be a multi-year project to migrate all capabilities into the AEDT IcePack. And we're quite excited about this new offering, and we're looking forward to delivering an improved IcePack with improved capabilities and fully integrated into the electronics desktop environment. And the goal here is to deliver users an improved overall experience with IcePack.